welcome to another video where we're doing data storage. So we've been doing the number systems and now we have to link all of that to the data storage. So imagine I give you a piece of paper and I ask you to write basically your name, or let's say I ask you to write your name, a picture. It doesn't make sense, but like just technically think about it. A song, the number 25, and a video. Right now we have learned how to write the number 25, but there's more to all of this, right? So you basically know how to write and draw all of these because you understand letters, pictures, and sounds, right? So you would know how to work out all of this. The computer basically does not know how to do that, and that's because a computer is made up of billions of tiny electronic switches called your transistors, right? So I wrote it down for you here. And then each transistor has only two states, so you can either have the off state or the on state. But the computer basically represents these as off state being equal to 0 and your on state being equal to 1. So with the transistors, think basically off means 0, on means 1 for the computer basically. And hence why everything is binary, and that's because it only has two things. So this means the computer's entire language consists of zeros and ones, and everything. By everything, I basically mean your numbers, letters, music, photos, and videos must eventually become a sequence of zeros and ones, and that's basically why we study data storage. Talk about the 5 types of data. The computer basically stores many different kinds of information, right? So we're just going to talk about these because it's mostly what we see. So you have your integer data, which is your real numbers, real integer numbers actually. You have your floating point numbers, your text, audio, music and videos, or images and videos rather. So to us, these are completely different, obviously, but to the computer, everything becomes a bit pattern. And now we're just going to talk about what a bit pattern is because we're learning bits, right? So a bit is basically one binary digits. If you think about it, you can either have 0 or 1, and that basically makes a bit, right? A bit pattern is simply a group of bits. So I have 3 examples here to show what I mean by saying groups of bits. So you're taking a lot of bits. Remember, bits is one binary digits. If you take all of those and put it in one group, you're forming a bit pattern basically. So think of a bit pattern as a sentence, just like letters combine to form words. Bit patterns basically also combine to form important information in the computer, obviously. For example, this bit pattern might mean the letter A, and this bit pattern might mean 15. With the one that means A, it can also mean an integer number. It can be anything. So a bit pattern might represent just information. But the computer itself doesn't know whether a bit pattern is a number, a letter, part of a picture, or maybe audio. So it only knows it has been given a sequence of bits, and the software basically tells it how to represent or interpret those bits. So let's talk about why we basically learned the number system, which is the previous videos that I've posted. And this is because basically most students, also me, I used to skip this, but it's the key idea basically. You think about it. Humans can naturally count in decimal or your base 10 because we have 5 digits. For example, the number 254, the computer only sees this as 2 electronic states, which can be your off and your on states, so it counts in binary. This means basically every decimal must first be translated to binary before it can be stored, right? Another example would be if you have 13, 13 basically becomes 1101 within binary. And because of that, now we're going to talk about the unsigned integers, which is basically what we've been doing when we were doing the whole number system thingies. So suppose maybe with unsigned integers, so right now we're doing number 4. Suppose you want to store the number of students in any classroom. You basically can't have something like, let's say, a negative decimal students. So you can't have a negative number of students. So there's no need basically to store your negative numbers, right? And hence why we use the unsigned integers, where the unsigned basically means there is no sign. So every number is basically assumed to be positive or 0. And then after this, we're going to talk about signed integers. Right now, we're talking about unsigned. So unsigned means you don't have a sign, and every time, obviously, you see something without a sign, you just assume that it's positive. So for example, if you have maybe this, so 4 bits or this bit pattern, 1011, using place values. So using place values, this is the same as 8 plus 0 plus 2 plus 1, which is basically 11, right? So it's unsigned because I don't have a sign here, and it does basically make sense. But what if I wanted to store in -11. So unsigned format cannot do that for us, which is why we basically now move on to the sign and magnitude. So after learning about the unsigned, which is what we've been doing when we were doing the number system, now we're going to learn how we store in signs. Okay, so think of a bank statement. So instead of writing maybe a whole number or a decimal number 500, you might want to use positive 500 or negative 500 to basically show if you maybe still have money or you maybe have debts, basically, right? So the plus here or the minus is basically your sign. So if you're thinking of sign and magnitude, the signs, the plus or the negative is basically your sign, and then the number itself is basically the magnitude. So the magnitude is like your 500 basically. And computers copy this idea. The first bit is basically reserved for the sign, and then obviously the rest of the bits are reserved for what the binary number is, right? So just kind of remember that. So with the first bit, if you're thinking of the signs, the first bits, if it's 0, that's always positive. Remember, when you had your unsigned, you didn't care basically what the first bit is. You would assume that it's a 0 or just positive, right? So right now, with the sign and magnitude, if it's 0, the first bit, if it's 0, then you always have a positive number. And if it's 1, you basically have a negative. Okay, so the remaining bits are basically stored in as the ordinary number. So any bit that comes after any of these two is basically the number that you want. And these two, if they are obviously the first bits, they will tell you what the sign of your magnitude is. So I have a little bit of an example for us here to look at. The first bit here is 0. So this basically tells us that the number is positive. And then the remaining bits are your 101, and this basically tells us what the binary number is. So this is a binary number we're dealing with, and if you were to convert it to its decimal form, you would have a 5. So because we have a positive, you would want to represent this as plus 5. You can do your in the base 10 system, right? Now let's take a look at this. So if I had, look at me writing negative. So if I had maybe 1101 and I was asked to maybe convert this to a decimal form using the sign and magnitude, I'd first have to look at the first bit, and that is 1. So this tells us this number, the number is negative. And then the remaining, our magnitude, so 101 in the base 2 is the same as 5 in the base 10. Representing this using sign and magnitude, I basically have negative 5. If you want to, you can do your in the base 10. So this is the different ways to spot if your number can be stored in as a negative or as a positive. And this basically is our sign and magnitude. But the sign and magnitude was basically rejected. And I have reasons here. So it was rejected because it creates two zeros. So if you think about it, with 0, the magnitude of 0 is basically 3-bit patterns of zeros. So if we wanted to know if the 0 is positive, one would say you can put a 0 as the first bit, the bit. And then if another person wanted to check if 0 can be negative, they can use a 1 there. And this basically means two zeros. But mathematically, positive 0 and the negative 0 is basically 0. So hence why it was rejected, and that's because it creates a problem like with the two zeros. So because it was rejected, they implemented the two's complements, and this method basically is used by most modern computers. I don't think computers would be assigned right now at this day and age to be using the sign and magnitude. So the idea here is to basically, instead of separating the sign from the magnitude or the number, the entire bit pattern changes. So to represent -5, we're going to start with a positive 5, and I'm going to explain why. So positive 5 is the same as 0, 1, 0, 1, right? And then it tells us to flip every bit. So basically 0, 1, 0, 1 changes to 1, 0, 1, 0. So yes, so you're basically changing everything to this. And once you flip everything, that becomes your ones complement. And then to make it two's complement, you basically add a 1. So you go +1 to the ones complement. So we don't care about the first initial positive 5 that was given to us. We care about the ones complement that we converted. And then to make it two's complement, you basically add a 1, and then you obviously calculate. So 0 plus 1, that basically is 1. 1 plus 0 is 1. And 0 plus 1 is 0, 1 plus 0 is 1. So cheat these as basically zeros, like you don't have anything there. So when you're calculating, you're cheating that empty space as a 0. And this is now -5 in two's complement representation. Remember, when we were doing the sign and magnitude, our -5 was basically 1101, and this is how they differ. So this is 2's complement, and this is the sign and magnitude. Sign and magnitude was rejected because it gives us 2 possible zeros, which is kind of incorrect, right? So you can't have 2 different zeros, and we use basically the 2's complement, which is the answer that we got here. And that's it for part 1 of data storage. Next time we're going to be looking at how pictures and videos are converted. We're going to look at the floating points and the ASCII table.